welcome to the stage Edward Beiting.
Thank you. My name is Edward Beiting, and let's see, do I have my slide up there? Do I press a button? Okay. My name is Edward Beiting, and my collaborator in this work is Dean Romine, who wrote all the data acquisition software for the data I'll show today. I focused my studies on excess heat from nickel-hydrogen systems solely. This talk will be a little different than the other ones because I'm going to show a number of systems where I did not see any excess heat, so all the results were negative in these tests. So what I'm going to do today is something a little different. There are 59 slides in this presentation, and obviously in 20 minutes I can't cover them all. The purpose of this talk is to make you aware of this work, and but to present it in sufficient detail that it allows critical review. So others who wish to pursue similar work or replication can use this work as a reference. I choose this venue to introduce this negative results because often negative results are not published, but I think it's useful to get some out there. So I'll show you what I've done, and it's open to criticism. So the presentation is divided into two main parts. The first part describes the calorimeter that I developed in the calibration system, and the second part goes through the four replication studies I did. The last one was not a replication study. It uses a formula that Technova used, but there was significant deviations. So we'll go through, I'll describe the technology that I used to measure the heat. I developed a technology for this originally for Parkhomov studies that I started. I was given a DARPA contract after I retired about 7 years ago from the Aerospace Corporation. And at that time, there was a lot of interest in the Parkhomov results, and I was paid to see if I could reproduce them. I had to develop a calorimeter that would take the high temperatures and expected heat that would be put out. There were no commercial systems available, so I developed a flowing fluid system that required just the two measurements, the temperature difference of the fluid into and out of the calorimeter and the flow rate. In this system, I redundantly measured the temperatures with a type K thermocouple and a platinum RTD with an accuracy of better than 1/10 of degree C. And the flow meter was a Omega Hall type flow meter that had a sensitivity of 0.13 cc's per second. This is a cartoon of the system in which it shows the cell that was used to do the Parkhomov studies, the high temperature cell, which is made of aluminum, and a Canthal heater on the end of it. This shows the calorimeter cooling system, which is a simple reservoir with a pump through the flow meter, a heat exchanger, and then the redundant temperature measurements in and out of the calorimeter and returning to the reservoir. This shows the calibration data that's taken. The calibration is done by an automatic sequence. It steps through 10 or 12 different temperature differences. In this data, it took about 26 hours to do. The first graph up there shows the pressure, the second, the temperature of the cell, the third, the flow rate. The fourth is the temperature differences. You see the temperature differences even for temperatures of the cells over 300 degrees or only a couple degrees C. The fourth graph plots the inferred temperatures with the inferred pressure, the inferred powers, thermal powers, for the input power. The black line and the sharp lines are the input power. The inferred powers are the curved lines from both of the temperature sensors. And if you subtract the two, you will see that you should be getting zero excess heat, which is the zero there. And you see there's about an hour to hour and a half time constant to read accurate temperatures. In this particular measurement, the accuracy was about half a watt, plus or minus a half a watt. This gives you data that you can look at your leisure, describing the cell calorimeter systems that were used for 3 of the reproduction studies. This is the instrument stack that I throw in there so you can look at the instrumentation that was used. The Parkhomov replication, at the time that I did it, there had been no replications of it, and DARPA asked me if I would try to do a replication of his work. And this was actually documented in a government report, which was published in 2017. This documents all the details of the high-temperature luminous cells that was used in this study. And these are basically the replication results. There were 10 unsuccessful attempts to verify the Parkhomov experiment. Only one of the 10 showed the hydrogen absorption profile that had been described by Parkhomov. The ability of nickel to absorb hydrogen depends on its chemical and physical surface. And I chose a type of nickel, which is Vale 123, that electron micrographs made look very similar to the nickel that he used. But cleaning this material didn't have an effect on the outcomes of the results. So the second replication that I attempted was taken from an EP report written by Brian Ahern in 2012. He was doing a lot of studies of nanoparticles and of refractory of zirconium oxide, but at the end of it, he did a study of pure nanoparticles of nickel in a cell, and he saw 50 times more power coming out from the other studies, and he recommended in that study that it should be replicated. I was able to obtain the exact material that he used, which is from a company called Quantum Spheres, which is referenced at the bottom here. These quantum spheres have diameters between 10 and 25 microns, and they have a thickness of 2.5 microns of oxide over them. The theory is that the 2.5 microns of oxide kept the material from sintering as it went to higher temperatures. My replication on this used a stainless steel cell, and I was never able to get any of the nickel material to absorb hydrogen. Without any absorption of hydrogen, it wasn't fruitful to go ahead and try to do calorimeter studies. So if anyone wants to repeat these, I actually do have some of this material available that I would make available to someone who wanted to try these. But this was, I could never get it to absorb hydrogen. Recently, there's been a lot of excitement with results from Mizuno, which were recently documented. Mizuno had a new technique of putting palladium in a nickel mesh by rubbing it onto the mesh. And he was able to, with 1,800 square centimeters of this treated mesh, be able to see 250 watts of excess power with a 50-watt input. And with the 300-watt input, he saw 2.5 kilowatts of power. So it was very exciting results. And to eliminate any variations of this material, the material I studied was actually provided by Mizuno himself. He gave me 2 samples of treated material, which I used in 2 separate studies. I basically took 900 square centimeters of the material, and I cut it up into 3 strips and put it in a reactor. So if I got, say, his 250 watt result, I would expect something of 100 watts of excess heat in my experiment. I increased the diameter of my calorimeter. This shows a calorimeter that I built to use this. This is an interior diameter of 10 centimeters. This shows the cartridge heater, the similar that he used in his studies. This is a standard Omega cartridge heater that goes down the middle. And it goes into a custom cell that I built to try to make it low thermal mass. So around the outside are the 3 levels of the nickel mesh, and in the middle goes the cartridge heater, and it allowed me to to measure the pressure during the experiments. This is a scale diagram of the cell inside the calorimeter. This system, there was a cleaning procedure that Mizuno did before the mesh was put in there, and this is the procedure that I followed for both samples. There was also a procedure to use inside the reactor, and so I followed his procedure also. This shows the calibration of the system used. This is similar to the data I showed you before. And after I did the calibration, I did a check of it, and it indicated that I had a sensitivity of about plus or minus 0.25 watts, a quarter of a watt. So the first run that I did was 200 hours, and the first part of this data was treating the material as, and then also treating it with hydrogen. The hydrogen, at the time, I did not have a pressure gauge for the readout on it, so all along this data is the pressures of the hydrogen that was used. The short story on this is that no excess heat was discovered. This slide discusses the previous data slide in detail. The second mesh, this is detailed steps that I took in treating the mesh inside the cell. And this was a 10-day data acquisition measurement. To the left of the vertical red line is the conditioning of it. In this case, I did have a pressure system with an output, and so the top curve represents the pressure the whole time. The next one is the temperature of the cells, and the next slide down is the comparison of the power in, the power in with the inferred power with the calorimeter. The bottom slide shows the excess heat, and there are certain levels, certain areas there that are circled in green, which shows it looks like positive excess heat, but I don't really consider it to be above the noise level of the acronym. It's less than a watt, so I consider this a negative result. This slide documents basically all the information you need to interpret the previous slide. Now, Mizuno emphasized in his work that the gas in there had to be certain purities, and he recommended that mass spectrometer measurements be made of the gas in there, which is what I did. I made a lot of mass spectrometer measurements. This is my mass spectrometer system. This is the vacuum system, how it was set up to use. And then I have a lot of slides on interpretation, the results, which you can look at. But getting to the results, I'll just point out two things. At the top, this system allowed a careful leak detection with a helium leak detector, which indicated it was tight. And second from the bottom, the H2O ion current was much less than specified by Mizuno. So I assume I was meeting all his criteria in these measurements. The final data is going to look at a Technova formulation of copper, nickel, and zirconium. I call this approximation because I did not follow their procedures for preparing it for reasons that I didn't have the facility to prepare a spun ribbon as required. It was during COVID and things were closed down. So what I'm going to do on this, talk about this approximation, is I'll talk about the materials that I used. I'll show you the experimental configuration, and then I'll look at the 25 days of data that I took. The material followed the atomic ratios of 1 to 7 to 14 of zirconium. This slide documents all the details of it. The second graph, or the second table down there, gives you the purity of the materials that we used. This material was mixed up and sent to a company called RCAST. It's in Maine, and they were able to arc melt this with a magnetic stirring into 8 buttons. Each button was between 135 and 188 grams, or 186 grams. Half of these buttons, I used their procedure of spraying these particles into an inert atmosphere. And when you do that, you get a dispersion of particles, of beautiful spherical particles. And I sieve these into different particle ranges. The particle range that I used for this one is indicated on this slide, which is particles from 20 to 38 microns in diameter, if I can read that correctly. So this is, so the processing of these particles, I took 4 ranges of particles and I put them in trays. And these trays I put in a furnace. And following the prescription by Technova, I calcinated these in the furnace for 7 days at 450 degrees C. I didn't know whether these particles were about 1 centimeter thick. I don't know whether the oxygen from the air would reach the bottom, but I was happy to see that basically all the particles changed color, top to bottom, didn't matter where they were, from light gray to black. And then I measured the increase in mass of the particles before and after and found an increase of mass of 1.33. And if you expected oxygen, all the zirconium in the sample to go to zirconium dioxide, you would expect a mass increase of 1.26, which I exceeded. So I considered those as, they actually surprised me that it worked so well, and I thought we might have a chance of making this material work. Recently, I was able to renew a collaboration with NASA Glenn, and they were able to do SIM EDS analysis of the particles. I'll just say, you can look at these at your leisure, but on the right side shows the before picture of the particles before they were calcinated in the oven for a week, and the left side shows broken up particles with inhomogeneous spread of zirconium and hydrogen on the outside. These were done by Wayne Jennings and under the direction of Teresa Bagno and Bruce Steinex, who I've known for about 10 years. So what I want to emphasize is this is not a replication study, because I changed completely the preparation of the material. Significantly, the particles were sprayed, and they were not taken from spun ribbon, which is, I think, the correct way to do, as you'll see in a minute. The first calcitation was not done of ribbon, but was done of these particles, which are thicker than the ribbon, and that's significant. And subsequent calcinations, they took all the material out, reheated it in the furnace. I decided to see if I could try to do it in the cell using pure oxygen instead of air. So those are significant differences, and that's why I do not consider this a replication study. This is a custom cell that was built to try to have low thermal mass for the material, for this material. This is the data showing the vacuum and cleaning specified. This was a 40-hour data run. This shows the gas loading. So after it was cleaned up, the material's in the cell, let's load it with hydrogen. So the top curve there is the pressure in the cell, and so when you go from vacuum to the spike, you see that where I pressurized it, then you see absorption, then you see multiple times that I pressurized and did absorption. The second cell shows the temperature, the second graph shows the temperature, and the third graph shows the excess heat. And there's something that occurred here that I haven't seen before, but during one of the searches for excess heat, you can see in the lower right-hand corner, I don't have a pointer for this, but basically you see endothermic. So after it's reached equilibrium and it's come up to zero excess heat, it actually cools below it in several places, which is interesting and worth studying. This shows the gas system for the H2 loading, and the amount of atomic hydrogen that was loaded in by the various pressurizations. This actually emphasizes that end of the gas of the data run that I did in the bottom curve, emphasizing where you see the endothermic reaction. But again, there was no excess heat that was observed. After this was done, I then tried to do a second calcination by introducing oxygen. And each of those peaks you see in the top curve are the pressure and absorption of the oxygen. And you can see throughout the whole thing in the bottom curve that there was no excess heat during these measurements. This shows the modified gas system that I used for the oxygen and also a secondary introduction of hydrogen, which is shown in this slide here. And again, during this whole process, the bottom slide shows that basically there is zero excess heat measured by the calorimeters. This is a blow-up of that data, but basically it hugs zero within the accuracy of the calorimeter. Now, I got this slide just a few days before I put this talk together. And again, this came from Wayne Jennings at NASA Glenn. So this is an electron micrograph on the left of the particles after the 600 run test. And you can see they're still broken up. And one thing I want to emphasize is you don't see any pitting or craters on this thing that you might see in a situation where you had excess heat. But actually the interesting thing is if you take one of these particles and you blow it up and see it split apart, you see this layering on the inside. And according to Wayne, when you look at this layering, very interesting, each layer alternates between high zirconium and oxygen and high copper and nickel. So it seems to be separated in the layers, which is really surprising to me, but if it really is this situation, you wouldn't expect nanoparticles in a refractory of zirconium oxide, and this kind of process is not what you'd want to do. So these are results from it. The only thing I'll mention is the last one, that no excess heat was observed. And the summary of this is that 4 replications or near replication studies were undertaken. They used a high capacity flowing calorimeter. None of the studies should be considered definitive. I don't want to discourage anyone to go and do other studies, but I think it's useful to get this data out there. All conditions of the trial were sufficiently documented to discover flaws. In the future, and now that we're back out of COVID, and NASA Glenn has spun some of my materials so I can do a closer study of the Technova stuff. I am processing that material. I've actually calcinated it in the lab already. But one of the things I'd like to do is try to develop a more sensitive calorimeter. One of the things I didn't mention is that the very first hydrogen, the amount of excess heat that Technova had in their first study at the coast, I wouldn't have been able to see. The second one I should have been able to see with a factor of 3 or 4 sensitivity, but I didn't see it. But as I said, it wasn't really a duplication. So these are the references used here. Thank you very much.
Thank you, Edward.